Okay, you can read the source out of Agarwal's text. You have a copy of this. You can see I've highlighted some things. First generation started out at 0.8 microns. Data rates of only 45 megabits per second. That's a DS3 for those of you who know that terminology. That's not too bad for radio, but it's pretty pathetic for fiber these days. So all of those pages are summarized in something we printed up for you. Okay, so first generation was near, that would be 800 nanometers, used gallium arsenide semiconductor lasers. These were lasers that had mirrors that were on the edge. So it's like a normal laser. You've got a mirror here on one edge and a mirror here on the other edge. But that meant that there's these kind of cavity modes that come in. Here's the gain profile. Here's the different wavelengths at which you can have amplification. But then just like plucking a guitar string, you have harmonics, right? So if the field has to be 0 at these 2 points, it could wiggle like that, or it could wiggle twice, or it could wiggle 3 times. So you get these cavity resonator modes. These are called longitudinal modes. And that messes things up. I want to be at one particular wavelength, not jumping back and forth between all these different longitudinal modes. So a better way of doing that is, came along later, better lasers. Put it this way, DFB stands for distributed feedback. Lasers, or a better laser. And these are diodes. They're like LEDs, except a lot cleaner. An LED would have a very broad spectrum. A laser has a very sharp spectrum, a very well-defined wavelength. In a distributed feedback laser, instead of putting the mirrors at the edges, it avoids those longitudinal modes by kind of a distributed way of making a mirror. So you put these little gratings like in an FPG, you put little scratches in it. And that causes the waves that are going back and forth to couple. So it works like a mirror. That's all. You can write it out. Distributed feedback laser looks like this as opposed to this, and so it gets rid of the longitudinal modes. So that was one improvement. Another major thing was rather than being at 800 nanometers like first generation, they said, gee, we'd rather be at 1310 nanometers or 1.31 microns, where the fiber losses were smaller. And that's where the conventional fiber had its 0 dispersion wavelength, so that looked good. So second generation moved over to 1310 nanometers, 1.31 micrometers. But then, let's see, what's the homework asking about? The loss here at 1.3 microns was about half a dB per kilometer. But less loss was achieved in 1979 at 1550 nanometers. Okay, so we're sparing you a lot of reading on the textbook to summarize it, and then I'm sparing you even more by summarizing the summary. Okay, so, but the dispersion, so let me kind of summarize that in terms of this little picture, loss. as a function of wavelength. It goes way up as you go into the visible. There's this little unfortunate OH spike, and then it's minimal loss at 1550. And then 1310 is wavelength in nanometers. 1310 was even better. I'm sorry, 1310 was less loss than the 800 nanometers, but 1550 was even less loss, 0.2 dB per kilometer rather than 0.5 dB per kilometer. This thing here is called the OH spike. H2O, we've all heard of H2O. So if you take some H2O, which is water, and you thump it and strip off one of the H's, then you're left with H1O instead of H2O. So that's an oxygen and a hydrogen atom forming a molecule. So that's because there's water in the room when you're making the fiber, water vapor. The only way you can get around this is you can remove that, the so-called dry fiber. The dry fiber is expensive because you have to remove all the water vapor from the room when you're fabricating the fiber. But then you can eliminate this OH spike. So people wanted to shift to 1550 nanometers because it had lower loss. But the dispersion for conventional fiber had 0 dispersion wavelength over here. So they came up with that curve that you saw of the dispersion shifted fiber, right? To have their minimal dispersion near this lower loss. And so then everybody moved over to 1550. And that's where they're at now. We're cranking up the data rate every time we get a chance. Then coherent systems are phase sensitive. We're going to just call that phi for phase sensitive. If you haven't seen this before, you're seeing it now. I don't have to just have amplitude modulation. I can have phase modulation, right? Remember your little trig, cosine of this angle, or this phase, phi, make this little vector spinner pointer of length 1, then the x-axis here is cosine of phi, and the height of that little clock arm, or whatever you want to call it. Electrical engineers call them phasers. The height along the y-axis is sine of phi. So from that little trig picture, you can draw what sine and cosine look like, and you can see that one's 90 degrees behind the other. I take one, shift it by 90 degrees, then I've turned cosine into sine. This is 90 degrees. 90 degrees, another 90 degrees is 180. I just turn +1 into -1. Another 90 degrees is 270. Another 90 degrees is 360. I'm back to 0. In terms of radians, that's halfway around pi, all the way around is 2 pi. So if I have so-called coherent modulation, and this is the latest craze, is coherent modulation, then I'm phase sensitive. Maybe I have these 4 different phase shifts, or maybe I have 8 different phase shifts. 8 dots on a circle is called 8 PSK. Phase shift key. Another thing I might decide to use modulation format would be to have, let's see, if I had a plus or minus 1 on the cosine part of the wave, and a plus or minus 1 on the sine wave part of the wave, then I'd have these 4 dots. 4 dots in a square looks just like 4 dots on a circle. But, so let's make it 4 level signal on sine and a 4 level signal on cosine. Now I have 4 times 4 gets me 16 dots. So this would be 16 QAM. Dots in a square is called quadrature amplitude modulation. There's AM, but there's AM on ancient history. Mathematicians called 90 degrees away quadrature for whatever reason. Right? And so that's where the Q comes from, quadrature AM. Just means I'm using sine and cosine part of the wave. So these higher level modulation schemes, what's the data rate? Data rate works like this. Let me go ahead and put that up here. It's true in general. If I just have 2 level AM, then every t seconds I'm telling you one of 2 things. That's 1 bit. Binary AM, data rate is the same number as the frequency bandwidth. It's just different units. So 1 per t seconds is 1 bit every t seconds. So instead of saying megahertz, I'm saying megabits per second. Right? In binary, that's the same thing. But what if I went to 4 level? Then I have a different data rate. In 4 level, now I have to uniquely identify these guys. So I want to call that 0, 1 again, I need to bring in another bit. Right. Now every one of these 4 levels has its own name in binary. So with 4 level, there's 2 bits of info. Therefore, my data rate is 2 bits every t seconds. Okay. So I just doubled the number of customers you can handle within the same frequency bandwidth. That's what's beautiful about it. We said frequency bandwidth goes like 1 over t. That's always. That's independent of my modulation scheme. It always scales that way. So you buy a certain amount of frequency bandwidth, maybe from the FCC if you're wireless, or you have a certain amount of wavelengths channel that you can use on your fiber. Right? Within that frequency bandwidth, you can increase your data rate by going to higher level modulation schemes. They don't have to be different amplitudes. Right? Could be different phases. Or could be different colors. I send you 1 of 8 different colors. Or they could be cats in a bag, right? Say I have, this is Fred, Wilma, Barney, and Betty. Right? So I've got 4 different cats, and you recognize each one of these cats. So every t seconds I put 1 cat in a bag, and I deliver it to you. You open it up and you go, oh, there's Betty. Right? How much information did you receive? You just received 2 bits of information. You just received the message 1, 1, for example. Or I could code it any way I want. I can write it list upside down or inside out or whatever. But each one of these 4 states is labeled by 2 bits of information. I'm busy, I'm recording, all right? Stand there and stare at me. Where was I? Okay, and if I was in 8 PSK, how many bits is that? You can take this same pattern and you can write it down again. I say, when in doubt, write it out. All right, there's 4 things. Write that down again. Then there's 8 things. And I need to bring in another bit to say, okay, here you're at the top of the stack, here you're at the bottom. So there would be 3 bits. I need 3 bits to point at one of 8 possible things. 8 different states. Whether it's 8 phases or 8 colors, 8 different cats, 8 different levels, amplitude modulation, whatever. Right? And in general, the pattern is Toolean responds to Toolean states. Then it's in bits. So 2 to the 3 gets me 8, right? And you can think of this also as 2 to the 3 being 2 times 2 times 2. 2 times itself, whoops, 2 times itself 3 times. I'm focused on that guy. Yeah, I'd like to talk to him, but not in the middle of a lecture. So I can do this 3 times, multiply again by 2, and it's 2 to the 4. 2 times 8 is 16, right? Indeed, this is 16 different dots. So what's the data rate here? 16, however you want to figure it out, is 4 by 4, which is 2 to the 2 times 2 to the 2, which is 2 to the 2 plus 2. I'm just showing you a wide variety of ways of counting. But however you want to do it, you can always just write it out. And I think it's very instructive to write it out, because then you can see why it all works this way. Right? However you do it, 16 is equivalent to 2 to the 4, so it's 4 bits every t seconds. But in PSK and QAM, I have to be able to tell the difference between sine and cosine in QAM. So that's a phase shift. I'm phase sensitive. Those are called coherent. Right? PSK, obviously, I'm phase sensitive. That's what's telling me my information. PSK, the amplitude never changes. Heterodyning and homodyning are also phase sensitive. And maybe we'll say more on that later. But that's why they're under this list of coherent modulation schemes. Okay. Well, just to kind of finish a point, obviously, can't get something for nothing. So why not just keep adding more and more levels? Well, I've got a certain amount of signal, and the width of my pin mark here is the certain amount of noise. And yes, I can always try to make my signal bigger, but there are limits, right? If I'm wireless, I start to fry birds. If I'm optical, I start to melt the fiber. Or other nonlinearities kick in before I actually melt the fiber. But you can see what happens. Put in 2 more, go to 4 level. Right? Well, it looks like I can still tell one from the other, but as I keep adding more and more levels, I start getting confused. Right? So I make errors. So the probability of error is also called the bit error rate. As a function of signal to noise ratio. Let's see, should this go up or come down? As I have better signal to noise ratio, I make less errors. Right? So I'll have some curve here for binary case. And as I cram more and more levels in there, what happens? At fixed signal to noise ratio, I start making more errors. So this might be 8 PSK. And then 64 QAM, 16 QAM, what have you. So there's a trade-off. You know, I'm cranking up the data rate in the same frequency bandwidth. That's wonderful, as long as I can get away with it. But at some point, I can't. Right? And typically, for example, I might have a bit error rate of 10 to the minus 3 would be barely tolerable for voice, right? But that would mean one error out of every 1,000. That's intolerable for computer data traffic, right? A banking transaction. Raw computer data, if it gets worse than 10 to the minus 6, you reroute the traffic. You do something else. You give up. You say this link is down, right? This would mean 1 out of every 1,000,000 bits on average is a mistake. Sounds clean, but if you got $1 million banking transaction going on, you don't want to mess that up. So you can think of this as like, let's throw that as the binary case. You can think of bit error rate as also like a quality of service guarantee. I'm going to guarantee my customers that they're going to get this good of a quality of service. Bit error rate's never going to get worse than 10 to the minus 6. So that's my constraint. Well, I could switch you to a higher level modulation scheme. What have you, 64 QAM is out there. 64 is 2 to what? Right? That tells you the data rate. So I can crank up your data rate if I have enough signal to noise ratio and still guarantee the same quality of service. Wireless people do this all the time. Depending on how close you are to the tower, you may have a better signal to noise ratio. It automatically switches you from a binary modulation scheme up to some higher level modulation scheme to crank up your data rate. It's not the matter of latency. It's not a matter of I'm closer to the tower, therefore the bits fly faster or any of that. It's a matter of signal to noise ratio. Okay. That's more than you need for the homework, but it's not just about the homework, it's about learning. Okay. Alrighty then. Was there anything else in here that you need? For the homework, probably not, but there's useful information in there, also nicely summarized. We talked about erbium dopant. We'll sneak this part in here. A comment relevant to homework. EDFAs. Erbium doped fiber amplifiers. Said right at day 1 that you can pump the electron in the erbium, so you dope the glass with a nice atom that you like its energy levels. Erbium has a nice energy level structure because you can pump it up to one of these little spin flip manifolds, and so it very quickly trickles down here. But then to make this jump, rather than just the spin flipping, this is like a atomic orbital transaction, so that hangs there for a longer time constant. So I pump it up to the top, it quickly trickles down to here, and then it sits there. So I pump this up with pump energy difference, and then this energy difference here corresponds to the signal that I want to amplify. now I've got this amplifier, right? So it's sitting here, it's been pumped up, and now I have this population inversion. One photon comes in. If I stimulated emission of radiation, it triggers this transition. So thereby it triggers the release of a photon corresponding to that color. That energy corresponds to a color. And so one came in and it's still there. It triggered the release of another one. One came in, two came out. It's an amplifier. And all I did was I shined a different color of light onto my glass to give it some power. Every amplifier has to be powered, right? So this one you power just by shining some pump light into it. And you're left on the homework to figure out, well, is this going to be a longer wavelength than that one or a shorter wavelength than that one? You know how to do that. This energy, let's write it this way, energy goes like Planck's constant times the frequency. The higher frequency photons correspond to more energy. You said that. If you're going from infrared to higher frequencies, into the visible, then into the violet, ultraviolet. Beyond that is X-ray. Beyond that is gamma ray. To have gamma ray frequencies, you have to set off a nuclear explosion or something with very high energy photons to create that high of a frequency. So the energy is proportional to frequency. Frequency times wavelength is some constant. Right? The phase velocity, speed of light in empty space. Okay, so you can answer that one, and you can learn some history there. And they're setting world records. Raman fiber amplifiers they're like DFAs. Maybe we'll sneak some details in on that later, but it works just like an EDFA. The atomic details of it are a little bit different. It's pretty impressive what we're getting up to. Terabit per second, it's amazing. But it also depends on what length are you talking about, right? So a lot of times it's not just the data rate, but it's data rate times the length. That's what gets your name in on the history books. Increasing that. So you know how to read. You got the details on that in there. Okay.